Hey everyone, this is Cheryl Wiygul. Today we're going to be talking about the moment of inertia. Inertia is the tendency to do nothing or to remain unchanged. If something is considered inert, it does not want to change. Newton's first law states that every object will remain at rest or in a uniform motion in a straight line unless compelled to change its state by the action of an external force. The tendency to resist changes in a state of motion is called inertia. Mass and area are the two types of moment of inertia, and area is the one that we're going to be looking at today. So how is moment of inertia relevant to us in construction? It's used to study the strength of structural beams and columns. It measures the effect of the cross-sectional shape of a beam on the beam's resistance to bending stress and deflection. The moment of inertia tells us how difficult it is to rotate or bend an object, such as a beam. We do not want a structural beam to sag. We want to use an X and Y coordinate system and select an X and Y axis around which the moment of inertia is the highest. The moment of inertia is proportional to an object's mass. A body's moment of inertia about any axis is equal to the product of that body's mass and the square root of the distance between the axes, as well as its moment of inertia about a parallel axis that passes through its center of mass. That is what the parallel axis theorem is, and that's what we'll be using to find the moment of inertia. So these are composite shapes, which are basic 2D shapes, and the parallel axis theorem must be used for these type of composite shapes. The first step is to find the centroid. The centroid is actually considered the first moment of an area. A line or axis of symmetry, shown on the first diagram, is the line that divides a shape or an object into two equal and symmetrical parts. The formula for a single area for the moment of inertia is area times distance squared. There are many different formulas for calculating moment of inertia, and they vary by geometric shape. This is just an example of some of them from our textbook. Here's an example of how to find the moment of inertia. This is a diagram of an I-beam, and you can see where it is on an X and Y axis, and the centroid, the center of it, has been found. So how would we calculate this? It looks like it is 3 rectangles maybe. But instead of making it into 3 rectangles, we could make it into one big rectangle and then just subtract the 2 small rectangles out of it. But the only time this method could be used is if the centroid piece part is on the neutral axis of the whole part. But otherwise, we would just use the formula and take the 14-inch base, the entire 14-inch base, by the entire 16-inch height, and multiply it to the 3rd power, and then subtract the 2 windows out of it, and then that would get the 3,051 inches. And then it's inches to the 4th power, which we already know that inches squared is area and inches cubed is volume. So inches to the 4th power is just like a measure of how far away it is from the centroid. And this is going to tell us like how strong it is, and that there's going to be less bending the bigger this number is. So now we're going to use the parallel axis theorem to figure this problem out. We're going to take away that big rectangle. We're going to draw out the 3 small rectangles. And we're going to number each piece 1, 2, 3. So each of the numbers is actually on the centroid, but we're going to have to move number 2 since it's actually on the neutral axis in order to do the parallel axis theorem. We moved 2 to 1 since 2 was on the neutral axis, and now we're going to use the parallel axis theorem to transform the number 2 centroid to the 1 by some distance, and that's why the distance is labeled on there. We're going to do piece number 1 from the equation. We're going to take 1/12 and multiply it by the base, which is 14 inches. Multiply that by the height cubed, which is 2 inches cubed, plus the area, which is 14 by 2, 28. And then the distance is going to be half of that, or it's going to be half of the second section and then half of the height of the first section, which is 7 inches squared. Now for the second piece, which is the center piece, we're going to do the same equation, 1/12 times 2 for the base and times 12 for the height cubed. And then that last part, the area times the distance, isn't relevant because it is on the neutral axis and that would make it 0. So that is all of the equation on that one. So piece number 3 is actually no different from piece number 1. The only difference would be the negative and positive distance, but since it's squared anyways, it would be an absolute value and that makes it irrelevant. So the way we're going to do this instead, so we're just going to multiply the number 1 piece by 2, and that will take care of the number 1 and the number 3 piece. So now we're going to add these up and we're going to come up with the exact same answer that we got when we did it the first way, but that is only because this was a simple problem that it was on the neutral axis to begin with. Though there are many more that are not going to be symmetrical or that'll go off the y-axis. Thank y'all for watching today, and if you have any questions, please ask this guy. Thank you.